Let's find out whether this series converges. When you look at it, you should already realize that it is very similar to the harmonic series, which is 1 over n. And so to see how similar it really is, we can look at the first three terms of this particular series that we're given. And the first term is going to be 1, because it is 1 over 1 to the power of 2, which is 1. I did the rest on the calculator. You can do them too. It's too time consuming for me to show it to you now, but I'll just give them to you. You have to trust me. 0.353, so this is actually 4. And then the third term is 0.2311. I did the fourth term as well, which is 0.1767. So you can clearly see that the terms keep decreasing and decreasing and decreasing. The only issue is this convergent or divergent? So that's for this series. And we're going to compare it to the sum to infinity from n1 to this series. And the terms of this one are, obviously it also starts with 1, but then the next term is 0.5. The third term is going to be 0.33333. The fourth term is going to be 0.25, right? Because these are just fractions. 1, 1 over 2, 1 over 3, 1 over 4. So clearly this one is always bigger than this one. Now this, unfortunately for us, is an issue, because the comparison test says if you have a series and you're comparing it to another one, and the one that you're comparing it to is divergent, and we know that the harmonic series by definition is divergent, because it's the p series where p is equal to 1. Unfortunately, this one is always smaller, so we do not know if this one is divergent or convergent. If the terms of this one were always bigger than the terms of this one, then we would be sure that this one is divergent. Also, if this one was divergent, and the term, you can also put it in these words. If all of these terms were smaller than all of these terms, then you would be sure that this one diverges, because this one diverges. Because if you graph this one, since it diverges, essentially you can say that the sum keeps getting bigger and bigger and bigger and bigger and bigger forever. Now this one, unfortunately, since it's always smaller, the sum is, you don't really know if it diverges, if it goes on forever, or if it levels off at a certain value. We don't know that. So we have to use the limit comparison test, which you can always use if your straight comparison test doesn't work. And in the limit comparison test, we say that the limit as n approaches infinity of the original function, and this is now going to get very messy. My pencil isn't even sharp enough for this. Divided by the one that we are comparing it to, which is 1 over n. We need to find the limit of this, and then when we see what the limit of this is, then we can discuss whether this is convergent or divergent, and I'm going to tell you the rules in just a second. So this then becomes equal to the limit as n approaches infinity of n over n1 plus 1 over n. And now this, if you were to plug in, actually you don't have to plug in infinity yet. I've just realized this actually is quite convenient. You have n over n to the power of 1 times n to the power of 1 over n. The n's obviously cancel, and now you can plug in infinity. And what you're left with is 1 over infinity, because it's infinity raised to the, oh, never mind. It's infinity raised to the power of 1 over infinity. So infinity raised to the power of 0, which is then 1. See, tricky. So actually you're left with 1, because we have 1 over infinity raised to the power of 0, or infinity raised to the power of 1 over infinity, which is 0. So the answer is 1, and the limit comparison test says that If you get a finite positive answer, and we got that because we got 1, then you can say that both of these are either convergent or divergent. And since we know that the harmonic series is divergent, then we can say, then both of them are in fact divergent. Therefore, the original series that we were given up here is divergent by limit comparison test. And that's all you have to say. It's sufficient. That's your answer.